Okay, so we've been talking about random variables. We just finished talking about the expected value of a random variable. Now we want to talk about the variance of a random variable. So they say that the expected value of a random variable gives us information about the long-term average value of x when the experiment is repeated over and over. So they say, but it doesn't always give us enough information. For example, they say, suppose a pharmaceutical manufacturer wants to buy automatic machinery designed for counting and then packaging 10,000 aspirin tablets in bulk containers. So they're buying some machine that's going to package large amounts of aspirin in big boxes or big containers. They say, since no production process is perfectly accurate, sometimes the device might package too many and sometimes not enough, of course. What criteria might the pharmaceutical firm use to judge the quality of the automatic machinery it tends to buy? One criteria is immediately obvious. Since the machine is designed to package 10,000 aspirin, it seems reasonable to require that over a long period of time, the average number of aspirin packaged should be 10,000. So if it's not close to 10,000, then maybe that machine is not so good for their purposes. More formally, if x denotes the number of aspirin packaged in a container, then we would want the expected value of x to be 10,000 or close to 10,000. This criteria alone, however, does not adequately describe the quality of the machinery. To see why, suppose we have one machine that works like this. So first box is like this, second box is like that, third box is like that, fourth, and so on. So here we can see that the expected value is 10,000. On the other hand, suppose we have a machine that works like this. First box has nothing, so it kind of completely missed the first box. Next box has 20,000, then 0, then 20,000. If you check the expected value of this, it would also be 10,000. So the criteria of using the expected value would say that both of these machines are the same. But clearly they're not both the same, and this one is much preferable to this. In both cases, the long-term average number of aspirin packaged is 10,000. However, machine A is obviously preferable to B since it is less variable in its performance, less changeable in its performance. Thus, not only should the pharmaceutical firm look for a machine that packages a long-term average of 10,000 aspirin, in other words, the expected value is 10,000, but it should also seek a machine for which the output is close to the average. Which most of the output is close to the average. In terms of x, the machine should have a high probability of producing values of x close to the expected value. In this section, we introduce a way to measure the variability of a finite discrete random variable, or just our random variable. So here we have two pictures. This one, sometimes we get -3, sometimes -2, sometimes -1, but the probability of getting something far away from the expected value here is clearly 0. The center is here. But this says that we have pretty high probabilities of getting things quite far away from this expected value. On the other hand, this one, we have much greater probability of getting something close to 0, close to the center. So we would say that this one is more spread out. This random variable is more spread out, and this random variable is less spread out. That is, x has more variability than does y. So they say, let x and y be the random variables whose probability functions are graphed up here. Since the origin is a center of symmetry for both of these probability functions, the two random variables will both have 0 as their expected values. You can see that basically 0 is the expected value for both of these. That is mu sub x. Remember, this means another notation for expected value of x, and this is another notation for the expected value of y, so they're both equal to 0. Observe, however, that it is more likely that random variable y takes on values close to the mean, close to here, than it is for a random variable x. For example, the random variable y takes on one of the values -1, 0, or 1 with probability this plus this plus this. What was that? 5, 2, and 2. So 90% of the time. Whereas random variable x takes on these values only this plus this plus this, only 30% of the time. Thus y takes on values within 1 unit on either side of the mean 90% of the time, whereas x takes on values within 1 unit of the mean only 30% of the time. We can summarize this idea loosely by stating that x is more variable about its mean than is y. Our next objective is to give a numerical way of describing the variability of our random variable about its mean. Let x be a finite discrete random variable. In other words, well, we already talked about what that means, with expected value mu. So let's suppose that the expected value is mu. If x takes on the value x when the experiment is performed, so if we perform the experiment once, we can define the difference x minus mu. So maybe mu was 0, we said in the last two random variables, last two pictures, but we don't necessarily have to get 0 every time, right? In fact, we see that the chance of getting 2 is 5%, and over here the chance of getting 3 is 30%, so we don't always have to get 0, the center. So we'll define whatever we get. Maybe we got 2 minus the mean. We're going to call that the deviation of x from mu. So in that case, 2 minus 0, the deviation would be 2. And that tells us how far the observed value x, so that's what we actually got, so they call it the observed value, is from the mean, mu. For example, a standard deviation of +3 means that x is 3 units to the right of mu, and a standard deviation of -3 means that x is 3 units to the left of mu. For most purposes, it is unnecessary and bothersome to worry about the side of mu on which x falls. For this reason, as well as others, statisticians prefer to work with this. So this might be positive or negative, but once you square it, it's only going to be positive. For example, a square deviation of 4 tells us that x is 2 units from mu, but does not tell us whether x is 2 units to the left of mu or 2 units to the right of mu. So if you haven't gone through some of the statistics videos that I have under my statistics page, where we talk about the standard deviation for a set of data, you should do that first before you go through this. But now we're talking about the standard deviation or the variance for a random variable. It seems very similar, but there's it's slightly different. Suppose now that x is a finite discrete random variable, and assume that we perform the associated experiment repeatedly n times. We're going to perform it a lot, many times. We observe n values of x, and for each of these n values of x, so it's like for example, if we're rolling a dice, so you probably remember that the mean, or the expected value for a die, is 3.5, which is right in the middle. So 1, 2, 3 are to the left of 3.5, and 4, 5, 6 are to the right of 3.5, and 3.5 is right in the middle. That's the expected value when we roll a die. But we don't always get 3.5. In fact, we never get 3.5, but we can get 4, we can get 5, we can get 6, and so on. So they say, so repeat this n times. For example, roll the die n times. We observe n values of x. So each time we get a dot, we get a number. Each time we get a number, like 1, 2, 1, 1, 2, 5, 6, whatever. And for each of these n values, we can compute the square deviation from the mean. For example, if we got 5, the deviation from the mean I just said is 3.5. So 5 minus 3.5. 5 minus 3.5 is 1.5. And then we square it. So we do that for each outcome that we got. So we roll the die many times. Each time we're going to get an outcome. We're going to take this minus that and square it. If we now average these square deviations, so we average them all up, we can produce a single number that gives us some indication of how the data were spread out. Right? So we'll get many different square deviations because we do it n times. We take the average of that, and that tells us the average squared deviation. So they say it's exaggerated because we squared it. So, we might get an average of 5, but that's the average squared deviation, not the average deviation. So they say, let's look at an example. So an experiment consists of tossing a fair die and observing the number x showing on the top face. Suppose after 4 repetitions of this experiment we get these. Since mu sub x is equal to 3.5, the squared deviations of the means from the mean, 4 minus 3.5, 3 minus 3.5, 2 minus 3.5, 3 minus 2.5 squared, we get all these. Then average these up, divide by, in other words, sum them and divide by 4. We get this, we get 0.75. On the other hand, if we had obtained these values, then the squared deviations would have been 4.25. So we could have gotten this, we could have gotten this. Since the dataset 2 has a larger average squared deviation than dataset 1, 4.25 versus 0.75, that is, this dataset has a larger squared deviation than this dataset, then we would say this dataset is more spread out around the mean than this is, which is basically true. You have things like 1 and 6. Here you don't have things so far away from the center being 3.5. Since dataset 2 has a larger square deviation than dataset 1, we would describe dataset 2 as more spread out or more variable about the mean than dataset 1. Now suppose that x is a finite discrete random variable associated with a certain experiment. We might ask if it is possible to predict what the average of the squared deviations is after n repetitions of the experiment. So now we want to predict this. Obviously we cannot predict this value exactly, since the values of x obtained in one group of n repetitions need not be the same as the values obtained in another group of n repetitions. Nevertheless, when n is large, in other words, when we do this many times, it's possible to make a reasonable guess about the average of the squared deviations. To see why, consider a finite discrete random variable whose only possible values are these 3 values. So not like the die where we had 6 possible values. Suppose we just have 3 possible values. And assume that the probability of this one is this, the probability of this one is this, the probability of this one is this. Suppose that in n repetitions, we get x1 occurring f1 times, x2 occurring f2 times, and so on. If we compute the squared deviations, we'd get x1 minus mu squared. That would occur f1 times. And this one would occur f2 times. This one would occur f3 times. So when we want to do the average, we could write it like this plus this over n, which can be written like this. And since these, that is this part, and this part, are close to the probabilities and get closer as n gets larger, in other words, since these represent the proportions of x1, x2, and x3 values in the n repetitions, it follows that when n is large, these proportions are likely to get close to p1, p2, and p3, the probabilities for x1, x2, and x3. That is, when n is large, the approximations, this is approximately that, this is approximately this is approximately this, should be good. Thus, from 3, we obtain the following approximation to the average. So instead of using this, we'll use p, which is the probability of x1. And this one we use p1, p2, which is the probability of x2, and p3, which is the probability of x3. So that's what it would look like if we had three possible values, x1, x2, and x3. That is, the average square deviation would look like this. Now they say more generally, if x takes on not just 3 values, but let's say k values with these probabilities, then we'll say the average square deviation when n is large is equal to, just like here, but we just extend it for more terms, it looks like this. And that's our approximation to the average square deviation. Okay, let's look at an example, and let's again look at the fair die example. So we toss a fair die. X is the number showing on the top face. Use the approximation that we just mentioned to estimate the average square deviation of the observed value. So we're going to use this approximation as the estimate for what we would get if we calculated the average square deviation for n tosses, for some n tosses. Then we get here, so these are the values that x can take, and these are the probabilities. They're all 1/6. So we do those calculations that we just had up there, but we put in 1 minus 3.5, 1/6. 2 minus 3.5, 1/6. 6 minus 3.5, 1/6. So we get that. We get this number. So this is an approximation for what the average square deviation is. So this is an approximation of the spread this is a measure of the spread of the random variable, which is the number of dots on a die. So this has a name, this thing that we've been calculating using the probability instead of the relative frequency here, and that's called the variance of the random variable. So it says if the values, these are the values that a finite random variable x can take, occur with these probabilities, then the variance of x, denoted by var x, or variance of x, is this, which is what we've just been saying. In other words, the variance of x is the sum of the square deviations of the possible values of x, times the probabilities of their occurrence. So instead of relative frequencies here, we use the probability, and that's how we define the variance of a random variable x. So now we can say, since we just calculated this above, that the variance of x, if x is the random variable of the die tossing experiment, then the variance of x is 2.92. And now this is going to give us a way to distinguish between those two aspirin machines that we had. We're going to say that one has a larger variance than the other, and that means it wasn't as good. So it had much bigger variance. Remember, the pattern for that second machine was that it packed 0 aspirin in the first box, and then 20,000 in the next box, then 0 in the next, then 20,000 in the next. So the variance is very, very high, and that makes it a very undesirable machine. Now we want to think about the fact that we squared everything, and so they say, since the variance formula involves the squares of the deviations, the units of the variance are the squares of the units of x. For example, if the values of x represent feet or meters, then the units of the variance of x would be square feet. Many people would prefer to have the variability of x about its mean. So we're trying to talk about the variability of x about its mean, be described by a number having the same units as x. This can be accomplished by taking the positive square root of x. The resulting number, called the standard deviation of x, is denoted by sigma sub x, or just sigma, when the random variable is evident. So sometimes we won't put the x there. Sigma is the lower Greek letter sigma, pronounced sigma. So sigma is the square root of the variance. So of course sigma squared is equal to the variance. So in the last example, we were taking the square root of this. So it's this. So this would be sigma of x, or the standard deviation of the random variable. They say that sometimes there's an alternative way to calculate the variance of x. They say, for example, suppose you had, again, these three values that the random variable can take on with these three probabilities. Then this is the definition, but they say this first term you can spread it out, this term you can spread it out, this term you can spread it out, then add them up. And then they note, you add them up, and I guess they collect like terms here. So they get this. And then they say, but what's this part here? That's actually just the expected value of x, so that's mu. And then they say, but what's this part here? That's 1, right? Because these are the probabilities, they have to add up to 1. So then substituting these things in there, we get 2 mu plus mu squared. So we can say it like this. So we can say this might be just easier to compute, so than doing it this way. But you could do it this way, or apparently you can also do it this way, and this might be easier. More generally, if x takes on the values x1, x2, xk, then of course you're going to get this all the way up to xk there. Okay? And so this is an alternative formula for the variance. So maybe this is going to be easier, and they say, let's try it. Do it for the same random variable in the die tossing example. So first they calculate the mean, which is 21 over 6, which of course is which is what we said, which is 3.5. And then they do the calculations, they get this. So you can check that yourself.